Okay, so good morning, everybody. We are going to start today the part concerning statistics, and you are going to see that in this part we are going to use what we have done during the probabilistic part. But first of all, okay, I want to record a little video that would be a kind of introduction to these topics. Okay, so first of all, we are going to do a little exercise, okay, with an inequality that is well known in mathematics and called the Markov and the Chebyshev inequalities, okay. And then on an example, okay, I will try to show you what will be the problems we are going to deal with during this statistical part, okay. So start. Okay. So the idea is to start with a little exercise to warm up. So, okay. We are going to prove what we call Markov inequality. Okay, so this inequality will work, okay, in grid generality. That is, okay, you may be continuous, discrete, or nothing, okay, and it works. So the inequality tell you the following. For all epsilon strictly positive, okay, the probability that the absolute value of x is greater than epsilon is less than the expectation of the absolute value of x over epsilon. Okay, and I want to write this, okay, for a random variable. I want all the terms to be well defined. So here I have a probability, no problem, and here I have an expectation. Okay, so I need to take x in L1, okay, here, just in order to make this expectation finite, okay. So the proof of this inequality is very simple, okay, and it is based on the following one. I said the following, that epsilon multiplied by the indicator function of absolute value of x greater than epsilon is always less than the absolute value of x. Okay, so it's an inequality that we are going to prove, okay, together. But suppose that it is true. If I have this, okay, I can take the expectation in this inequality, okay, because I know that if z is greater than y, okay, and that the expectations are well defined, the expectation of z is greater than the expectation of y. So from this one, okay, I can deduce that the expectation of the absolute value of x is greater than, so by linearity, I can remove epsilon from the expectation. I have the expectation of the indicator function, and we have seen together that the expectation of an indicator function, remind you, of it fulfills, in fact, Bernoulli distribution. Okay, so I am able to compute this expectation that is just by the associated probability of the set. This one. Okay, and you see that this inequality here is exactly this one, because my epsilon is strictly positive, so I can divide by epsilon and it's finished. Okay, so the Markov inequality, okay, is a consequence of this little inequality here. Okay, so I have to prove this one. Okay, and the fact is that I have here an indicator function, and what I know is that my indicator function here is a mapping from omega into 0, 1. So it can take only two values, okay? That is equal to 1 if the absolute value of x of w is greater than epsilon and 0 otherwise. Okay, so in fact, if I want to prove this inequality, I have to prove it, okay, in two cases: the case where the indicator function is equal to 1 and the case where the indicator function is not equal to 1. Okay, so let's do the job. So I have this inequality here, and I am interested in what happened. So first case, so if the indicator function is equal to 1, that is this condition. But what we have in this condition? In this condition, I know that the indicator function is equal to 1. So my star inequality here is equivalent to say that epsilon times 1 is less than the absolute value of xw. So what I want to prove, that is this inequality is just a consequence of the fact that I am in the case where this is greater than epsilon. Okay, so nothing to say in this case. Very easy. Second case, okay, but the case where I am in this situation, that is the indicator function is equal to 0, okay? So if the indicator function is equal to 0, what I have here, but I have epsilon times 0 less than absolute value of x of w. And of course it is true because here I have an absolute value. So an absolute value, and this one is equal to 0. An absolute value is always positive, okay? So I am in the situation where, in the second case, okay, the inequality is also obvious. So in both cases, okay, my inequality are okay. So I have this one, and taking the expectation, I obtain what we call the Markov inequality. Okay. So it's the first inequality I want to deal with, and the second one, that is called Chebyshev. So in the textbooks, okay, you will see that you have a lot of possibilities in order to write Chebyshev. Okay, I will use this one. Why not? Okay, most important is to know what is the meaning of this inequality. So this inequality tells you the following: for all epsilon strictly positive, okay, and for all x. So here I impose a little bit more conditions than the previous one. Instead of supposing that x is in L1, we are going to suppose that x is in L2, meaning that I am able to define the variance here. Okay, x in L2. Okay, and I have the following, okay, that the probability that x minus the expectation of x is greater than epsilon, okay, is less than the variance of x over epsilon square. Okay, so you have the possibility to control the probability that, okay, the absolute value between x in its expectation, okay, is greater than epsilon, okay, through the variance. Okay. To remind you that we have seen together that the expectation is the best approximation of x by constants, okay? And the variance allow me to control, okay, in some sense, the quality of these approximations through this kind of errors, let's say. So to do this proof, let's come back to the previous inequality we have seen together. Okay, so I know that when I am in L1, and when I am in L2, I am in L1, so I can apply, okay, so the Markov inequality, and keep in mind that I have, okay, for all, let's say y belonging to L1, okay, we have this. I have this one. Okay. So let's do the job. So what we are going to do? Okay. So the idea is to make appear the variance on the right part. Okay. So we are going to take y that is equal to, in fact, we are going to take y equal to x minus the expectation of x square. Okay, we are going to take this one. Why not? I have the right, because if my x is in L2, necessarily this quantity is in L1. Okay, so this one belongs to L1. So I can apply the Markov inequality that tell me the probability that the absolute value of x minus the expectation of x square is greater than any epsilon is less than, okay, what? But the expectation of this one, the expectation of the absolute value of this one, but this one is positive. So the expectation of this one, that is just the variance of x over epsilon. Okay, so I have this inequality here. That is not exactly the equality I want. Okay, we are not very far, but it's not the equality I want. So what I remark that this probability here, because the square mapping is increasing, okay, on R plus, this probability is equal to the probability that x minus the expectation of x is greater than the square root of epsilon. That is less than the variance of x over epsilon. But if I define an epsilon tilde equal to the square root of epsilon, epsilon is an arbitrary number that is strictly positive. So the same holds for epsilon tilde. And if I do this, okay, what I obtain, but I obtain exactly what I want. That is that the probability that x minus the expectation of x greater than epsilon tilde is less than the variance of x over what? So epsilon here, I take the square to make appear epsilon. That will be epsilon tilde square. And this is exactly what I want to prove. Okay, so you have two inequalities. In fact, the second one being a consequence of the first. Okay, that allow me to control the probability that, okay, x and its absolute and its expectation are close together or not. Okay, so it measures the quality of the approximation of x by its expectation. And I keep in mind that expectation in the best thing I can do if I want to approximate a random variable by a constant. Okay, so I have these two inequalities, and you see that in fact, very simple to recover. It's based on this little inequality here that is very easy to prove taking cases. Okay, so you are going to understand in a few minutes, okay, why I have done this, okay, in order to start the part concerning concerning statistics. Okay, so what we are going to do now, okay, is to try to give a little presentation to what we are going to do in the three sessions, okay, related to statistics. Okay, the one dealing with what I have called sampling, the second one being more focused on estimation of parameters, and the last one being devoted to testing hypothesis. Okay, and I want to start with an example in order to illustrate what can happen. We are going to flip coins once again, okay? So we are going to flip, okay, a coin several times, let's say n times. independently. Flip a coin n times independently. Okay, I denote by xi. Okay, the random variable that is 1 if head appears on the ice toes. Okay, and 0 if tail, in fact. Okay. Okay. And what I can say from my hypothesis here is that, okay, I have x1, xn, okay, that are independent random variables following. So what is the underlying distribution here? It's a Bernoulli, okay, with a parameter p. Okay. And here, the only thing we are going to suppose is that, in fact, my p is not, change nothing, but okay, I have a real coin factor, so meaning that the two events may occur. Okay. So what we are going to do in statistics, or which kind of question we are going to answer, okay, in the parts concerning statistics, okay? First question. From, okay, experimental observations, so meaning that in your room, you take a coin, okay, and you flip it and you, okay, write, okay, what is the issue of this experiment. So from experimental observation, okay, we want to approximate P. Okay, so you flip a coin n times. Okay, so suppose that you have time and you do it, okay, 100 times. But is it possible from this observation to obtain, okay, approximation of P? That is, okay, the probability that head occur, okay. For example, if you want to answer the question that, okay, is the coin fair or not, okay, or something like this. So from experimental observation, we want to approximate P, okay. Secondly, we want to question the quality of our approximation. And if possible, okay, is it possible to distinguish, okay, among all the way to approximate P, one that is optimal in a sense that we are going to precise, okay, but okay, we want to be able not only to compare between different approaches, okay, but we want also to be able to know if it is possible to one that is best among the set of all the possible approximation, okay? And the first thing that we are going to do, okay, is to test some hypotheses concerning P. So something that is not completely different than the true previous one. But for example, okay, we want to know if P, let's say, is greater than 1/3. Why not? Okay. Or if P is equal to 1/2. Okay. Or P between 1/3 and 2/3. Okay. And we want to have, okay, rigorous mechanism in order to be able to check if these hypotheses are plausible or not. Okay. So you have here 3 questions that will be more or less, okay, the 3 courses we are going to do. So in the last, it will be the part concerning tests. Okay. The second one will be the part concerning estimation. And the first one, okay, that is sampling. And sampling will be something that will be particular, so it can be seen as, okay, a special case of this one, let's say, okay, and even a special case of this one. It will be to question or to answer this kind of question, okay, when, if I suppose that P is an expectation, okay, so P an expectation, that is exactly the case we are going to deal with now, because I know that Bernoulli has an expectation equal to P, okay? So in fact, what I want to approximate from my observation here is just the expectation of my random variable, okay? So sampling will answer to this question, okay? How to approximate an expectation from observations, okay? And we will also answer what happens when P is a variance. So in the part concerning sampling, okay, we are going to see how to approximate, okay, the expectation and the variance of a random variable from observations. And by observation, I mean, okay, independent observation of the same distribution as when you flip a coin several times, and okay, then that do you not, okay, which issue you obtain at each flip, okay. And typically here in this situation, we are going to see that I can see things in the general case, how we are going to do just now in my example, okay? And we are going to see what happened, okay, in order to approximate the expectation and the variance of a Gaussian random variable. And we are going to see that we will have nice properties in this situation, okay? So to conclude this little introduction, okay, I just want to finish my example and to say what can I see, okay? So we have remarked that, okay, so I have my observations here, okay? My observations that are independent one. And I want to approximate my P, okay? Knowing the fact that in this case, P is the expectation of each of them because the Xi follows the Bernoulli of parameter P, okay? So one natural approximation in this situation, and it's something that we are going to start to study, okay, you will see in the next video, okay, is to say that, okay, P is the expectation, okay, so in some sense, the average value of Xi here, okay, and what we are going to do, we are going to approximate my P by, okay, the mean of all my observations. Okay, and I denote, it's a notation that we are going to use deeply in the statistical part, this one by Xn overline that I will call the sample mean. Okay, so why this is not a bad idea to do this? But first, because if I take the expectation of xn over line, okay, using the linearity of the expectation, I have the expectation of the mean that is equal to the mean of the expectation, all the expectation being the same here, and I recover P. Okay, so if I approximate my P by this xn over line, I know that in average, okay, this xn over line is equal to P. Okay. Okay. So I have this. And now my idea is, okay, I have a natural candidate for this approximation, and I want to check, okay, if it is possible for me to have a look on the quality of my approximation, okay, of the quality of my approximation. And in fact, I can have a look on the probability that the absolute value of xn over line minus P is less than, oh, excuse me, I will do it in the second step, but for the moment, greater than epsilon. Okay, so I want to control this probability. That is in some sense the probability that I do a bad approximation because, okay, the difference between these two is greater than a particular level. So from the Chebyshev inequality we have seen together, so from this inequality here, from the Chebyshev inequality, okay, Chebyshev, I know that this is less than what? Then the variance of xn over line minus P over epsilon square. So here what I have, okay, so I have a constant here, so I can remove it. So it's the variance of xn over line here, okay, because when you add or subtract a constant to a random variable, of course it changes nothing to the variance, okay, over epsilon square. And what is this variance here? So it's the variance of 1 over n, the sum from I equal to 1 to n of the xi, okay, over epsilon square. So what I have here, first I can remove 1 over n from the variance, and I will obtain 1 over n square. And then I have a variance of a sum, but I have a variance of a sum of random variables that are independent. Okay, I have independence between x1, x2, and xn. So the variance of the sum is equal to the sum of the variances. Okay, and I know that all the variances are equal. So I have, in fact, here n1, n times the variance of x1 over epsilon square, that is equal to the variance of x1, okay, over n epsilon square. Okay, so I have this one, and I know what is the variance of x1 because x1 follows the Bernoulli of parameter p. So if I continue my computation here, the variance here will be equal to, okay, p times 1 minus p over n epsilon square, okay? And here I am in the situation where p belongs to 0, 1. So if I plot here p times 1 minus p, I obtain something like this. Okay, and okay, we can see that this mapping here has a maximum at 1/2 here. So I can say that this one is less than 1/4n epsilon square. Okay, just studying this mapping here, it's the mapping P1 minus P. You can study it and see that the maximum, okay, over the interval 0, 1 is reached at 1/2. Okay. So I have this one. So let's copy what I have proved here. I have proved that the probability that xn overline, that is my approximation minus what I want to approximate, okay, greater than epsilon is what is less than 1/4n epsilon square. So in the same way, since I have this one, okay, I can say that the probability that xn overline minus p greater than epsilon here, or I can put, if you want here, a strict, okay, is less. So I just take the complementary set. This one is the complementary set of this one. So I obtain something that is the probability. So if the probability of the set is less than a level, the probability of the complementary set will be greater than 1 minus 1/4n epsilon square. Okay. So the probability in some sense that, okay, if I take my epsilon to be small, okay, it's the probability that my approximation and P are close together, okay, with an epsilon that may be an arbitrary epsilon, arbitrary small, okay. So I have this one. And let's say that, okay, something that we are going to fix in the second, okay, that you want that the probability to be less than epsilon, okay, you want it to be greater, let's say, than, why not, 95%, okay, it's a level that you impose, okay, you can also impose if you want 99%, okay, but I will do the computation in this case here. Okay, so suppose that you want to be sure with the probability of 95% that, okay, the distance between xn overline and p is less than epsilon. So if I do a little picture here, you have the p that you want to approximate. Okay, you have here p plus epsilon here. You have here p minus epsilon, and you try to compute the probability that your approximation lies, okay, in this interval here. So you want xn overline, okay, between p minus epsilon and p plus epsilon, okay, and you want it to be equal to 95%. So of course, if you want to do this, okay, it will depend on the precision you want here, epsilon, and on the n, that is the number of clips you have done, okay? And I can tell you just it's a numerical approximation. So if I want epsilon equal to 0.001, that is, okay, the size of my little interval around p here being equal to 0.02, okay? Or if I want epsilon to be 0.0001, okay, I say that if I want this kind of precision or this kind of precision, okay, my probability will be 95% here, okay, so I will obtain 95% in star here if n is in fact equal to, okay, 50,000. So it means that if you want to obtain such a precision, okay, with the approximation of P flipping coins, okay, but you will have to do a great number of flip, okay, if you want to obtain such a precision here. And typically, okay, for a precision that is also better, so I will obtain the same thing if n is equals to here, so 5 times 10 to the power 8. So it means that here, if you want to obtain such a precision with this methodology here, you need to have time, okay, in order to do, because, okay, you will have to wait a long time before to be able to flip the coin, okay, 500 million, in fact, times, okay, in order to obtain this level of precision. Okay, so we have this. So, and what we are going to do, so in the next part, okay, is typically to generalize this kind of process, okay, in more general situation. And we will do this, okay, in three parts. First, the sampling part that we are going to start just after, then the estimation part. That is a general framework, in fact, that is a more general case than the one concerning sampling, where we are going to be interested in expectation and variance, approximations of expectation and variance in the sampling part, and typically when you have Gaussian random variables. And finally, we are going to test hypotheses concerning, okay, some parameters of particular distributions. Okay, so see you in a few minutes to start, okay, the course concerning sampling after this little introduction. Bye.